So most frequently you'll be doing what we did in the previous video, which is calculating a difficult line integral and using Green's theorem to make it easier, to make it a double integral that turns out to be easier to calculate. You can actually go backwards too. You can use Green's theorem in reverse to calculate area. So let's just look at this. We have integral over some region, qx minus py dA, is equal to integral of the boundary of the region of the original vector field q comma p. Or actually, let's write another version. We have p dx plus q dy. And that's going to be the easy version to work with here. Okay, so what are we doing when we're calculating area? Area is the integral over the region of 1 dA. So that means I want qx minus py equal to 1. So I have to create some functions, p and q, because in a calculate the area problem, I don't have a vector field. So I'm going to make a vector field to make this work. So one easy one that I like to do is if I just write q equals x and p equals 0, then take the partial derivative of q with respect to x, that's 1. Partial derivative of p with respect to y, that's 0. So I get 1. Another easy one is q equals 0 and p equals negative y. Some people like to use q equals 1/2 x and p equals negative 1/2 y. There are infinitely many combinations that work here. And so what I can do with any of these, I'll just do it using the first one. Now this is the integral over the boundary. Oh, I should have written r here. It's good if my region doesn't change letter names. Of p dx plus q dy. But now that qx minus py equals 1, I actually chose q and p. And it turns out whichever one of these you choose, the answer is going to be the same. That's the beauty of Green's theorem. Okay, so then this is the integral over the line integral over the boundary of the region. P is 0, so that part is 0, and I just have x dy. Okay, so let's do an example. Let's do an easy example. We're going to calculate the area of a circle of radius r. So we know what the answer should be. It should be pi r squared. And we'll make it centered at the origin. Okay, so let's call the circle big R. So I have the region big R, 1 dA, and then, as I said above, that should be equal to the integral over the boundary of the region of take any functions q and p such that qx minus py equals 1. So I'm going to take my same ones I had before. So q equals x, p equals 0, and I have p dx, which is 0, and q dy, which is x dy. Okay, what does that mean? That means I'm integrating over the circle, so of radius r, so that's r cosine t comma r sine t. That means x is r cosine t, and t goes from, if I take t goes from 0 to 2 pi, I get, let's just say 2 pi, I get a positive orientation, right, going that way, so that's good. Just have to make sure all the orientations are positive. X is r cosine t, and then dy is derivative of y with respect to t dt. So I have another r cosine t dt. Okay, what happens there? I can pull out an r squared as a constant, and then I'm integrating from 0 to 2 pi of cosine squared t, which, if I look at this trig identity, we should be pretty good at this now. I can solve for cosine squared t is cosine 2t plus 1 over 2. So I'm integrating from 0 to 2 pi cosine 2t plus 1 over 2 dt. So r squared, and this is negative sine 2t over 4. I have a little chain rule in there, plus t over 2, and then I'm going from 0 to 2 pi. So sine of 0 and sine of 4 pi are both 0. So I'm just left with, really, it's when I plug 2 pi into here, that's the only term that's not 0, so I get pi. So that's pi r squared. Okay, that's good. So maybe using a machine gun to kill a fly, but we've used Green's theorem to prove that the area of a circle of radius r is pi r squared. And really the point of this example was so that you're convinced that it works.